Okay, in the last video, we covered the initial function to create the data. Now we're going to look at how to actually do some of the likelihood ratio tests in this video. So we're going to start from the beginning here. We're going to load some libraries we need, the psych library, the lessR library, and probably most importantly, the MERT library. And I've got a function here that is totally optional. What this does is it basically takes the output from MERT's default function. And this is just a custom one I wrote to kind of clean it up and just sort of organized items into diff and no diff items. So I'm not going to go through a ton of what's going on here, but really it's just manipulating the output that you get out of MERT. We may come back and look at it a little bit later once we get to that stage of the program flow, but for now we're going to ignore it. We do need, however, to load in our make data functions since I cleared everything out. And again, what we're doing here is we're making data with 1,000 per group. So this is really kind of n per group. And we're going to call that function that we just loaded in here. And that function, remember, creates some generic item parameters, A parameters, and some of those D parameters, which are kind of like the B's, linear transformation of the B parameters. And it makes it for two groups, and then it modifies them for the second group to be one higher than the first groups for items 13 to 15. So we know the diff items are items 13 through 15, and the other 12 items should be A-OK and no diff on them. So anyway, that's what we get. We get back a data set with those 2,000 people, again, 1,000 per group. And we're just going to, first off, sort of make some labels here. We're going to make a label called group. And essentially what we're doing is this is going to be a string or an element, not a string, sorry, a vector, an array that is 2,000 long, and for the first 1,000, it's just going to be 1,000 of the refs in a row. Think about arrays again as sort of boxcars. The first 1,000 of those boxcars are just going to have the word ref for reference group, and the second 1,000 is just going to have the letters foc for focal group, and that's what we have done here. And then what we're going to do is we're going to parse the data out. The focal group we're going to set to the first 1,000 cases, and the reference group the second 1,000 cases. So that's the way we have done it. And so the reference group parameters are going to be the ones that are, or the D2 up here that are 1.0 higher than the focal groups. So I'm not going to run through this code too much. This is just some stuff that we've done, before that's not really related to the likelihood ratio test. Just checking the dimensionality of the data. It should be unidimensional. You can run it really quick if we want to here. The plots are not going to work for me, of course, but we should see if we output that properly that it is unidimensional. And same with the other things down here, checking model fit. We really haven't gotten there in the course, and that's what this video is about, and as well with plotting. So all this stuff is sort of, stuff you would do in your actual program flow, but we're not really going to talk about here. We're going to get right to the likelihood ratio test. There is one command we're going to run, though. This is MERT cluster and 4. So most of your laptops and other modern CPUs have multiple processors in them, or at least processors that they're able to use kind of multiple aspects of the processor. I don't really know, I'm not really a hardware guy, but essentially what this is saying is instead of using just one of your processors, use 4, and that should greatly reduce the computation time for some of this stuff. And that's all we did there. We just loaded that up. At the very end of the program, we've got a MERT cluster remove equal true. That gets rid of that, so it kind of frees up your resources back for whatever it is you normally do with them. But we are going to run that part. So let's take a look then at some of the models we actually might use for diff. So we're going to start with a completely free baseline model. And this is not part of the likelihood ratio test, but it is useful to look at your item parameters. So we're going to run this model, and we are going to run in MERT, there's a command called multiple group. And that's what you need to use for any kind of test of diff or differential functioning, invariance, what have you. And we're going to feed it the 2,000 case data set, the full 2,000, and we're going to tell it one factor, and we're going to use group to specify the grouping variable. And the group is that vector that's 2,000 long, which is the same size as the data, where the first 1,000 is the word ref and the second 1,000 is the word foc, and we're going to run that. And this will take just a minute to run here relatively quickly. And then we're going to just print out the coefficients. So we're going to take the call the coefficient function from the MERT package, give it this model we just ran, and we're going to ask for simplify equal true to get our usual, A, B, or not A and B parameters, but the B parameters, not the D parameters here. If we run that, let me pull up the output here just a little bit. What you can see is we get two sets of item parameters, and two factor means, two factor covariances. This is two because we have two groups here. We specified a multiple group model. So this is the model where things are run completely independently, right? So if you look at what has happened, you can see for the first group, the factor mean was set to, the latent mean was set to 0, and covariance, which is just a variance because it's like a covariance matrix. There's only one thing in it, so it's a variance, is 1. So you can see the program's defaulting to setting, kind of identifying the model by making the latent mean 0 and the latent variance 1. And it's doing this for both groups. So this is telling us these groups are really not linked in any way, right? So if one group happened to have a higher mean, latent mean on this construct than the other, um, we wouldn't really be able to detect that because both latent means are being set to 0, and then the item parameter estimates, that we have here, kind of based on that. That's sort of the metric setting that's happening here. So we can't really compare these directly for diff, but it is useful to at least have a look at what the item parameters look like in each group separately. This essentially just saves you from running, the MERT program separately on those two data sets we created. You could have very well done that as well, but you can use this multiple group here to do the same thing. These models, again, are not going to be, you're not going to be able to look at diff necessarily from them, but I do think this is useful for kind of rounding up the item parameters and putting them in your manuscript. So a lot of times I'll put, in the manuscript, this is the item parameter for group A and group B, and just kind of make a note that they're not really necessarily linked here in any kind of way. Again, using the coefficients. I'm sorry, I misspoke earlier. When I said the simplify equal true gives you the B parameters, it does not. That's the IRT params function that gives you that. I don't know if you can actually use that. Let's see if I can, what is IRT parm? Okay, so in any case, it's going to give us the item parameters here for both groups estimated independently. That's for the manuscript. That really doesn't pertain to the likelihood ratio test at all. And to do the likelihood ratio test, we're going to start and use the, initially, like we talked about in the last video, use the all others as anchors approach first. Okay, before we get going with actually conducting some of the likelihood ratio tests, let's step back and take a look at the big picture really quickly. So what are we trying to do here? Well, the main thing we're trying to do is we're trying to test items for diff across group. Do the items function differently by group? And if so, that may be a sign of item bias like we talked about already. So for the likelihood ratio test, to test for diff, you test one item at a time and you compare two different models that are nested. And we talked about that already as well, where one model is sort of a special case of another model. So if you take a free model and then you start constraining parameters, that'll be nested inside the free model, and vice versa. But those two things are nested within each other. But in order to do this, we can't just start having at it. We need to first link the groups. And we had a whole unit on linking. We talked about the need to really identify the model, right? You're trying to estimate both datas and item parameters simultaneously. We've got to identify the model somehow. And typically the way we do that, if it's a single sample, is we just set the latent mean to 0 and the standard deviation to 1, and then all the model's identified and all the item parameters can be freely estimated. That doesn't work in a multi-group model, though, because it requires the assumption that the two groups actually have equal distributions of latent data, which is oftentimes what you're trying to test to begin with, right? You're trying to see if there's a difference between two groups in some variable, so you're certainly not assuming that the two groups are the same in that latent trait. So that doesn't work. So we need to actually do something involving some anchor items. So we're going to specify items that we know are good and are identical across the group, that function identically, and we're going to use that to set the metric, and then we're going to test the other items. So how are we going to do that? Well, probably the most obvious idea is to say, well, whatever item you're testing, we'll just make all the other items anchor items. So everything is constrained to be equal across all the items, and then we'll free the parameters for one item, and we'll test it for diff, and then our metric is set by all the other items. So we've done a really good job here. There's a couple problems with that, though, and one is if the anchor items actually have diff, then that diff can effectively be sort of transferred onto the item you're testing. And it typically results in too many false positives. In other words, you'll find items that don't have diff that look like diff items when you're doing the all others as anchors. So that's kind of where we got to with the approach from Mead and Wright. Let's talk about the A5 approach. And there's two steps here that actually use a fairly almost opposite type of likelihood ratio test. And I just want to be clear on what we're doing. So step one is just all about finding anchor items. We are testing for diff in step one, but we have no interest whatsoever in the outcome other than to select the anchor items. So you wouldn't really report that. You wouldn't really talk about it. You would just get, use it to find anchor items and then move on to step two. And step two is actually conducting the diff test. Okay, so step one, we want to try to find some suitable anchor items, and the anchor items need to be diff-free. So we need to test items to see if there may be diff there, and if there is obvious diff, we'll just rule those items out from anchor items. Now, we've already talked about how the all others as anchor approach is not great, but it's suitable for kind of getting the thing started, to get the process started in order to just find the anchor items, right? So that's what step one's all about. So we're going to use the all others as anchors approach. The baseline model here is constrained. And in this baseline model, all the items have the same item parameters across groups. And it's a constrained baseline model. And then the comparison model, you free up parameter for just one item. And those are going to be distributed as chi-square. You get a p-value. You'll do that for all the items, and that will give you an initial test of whether or not there is diff in the items. And we're only using results of this to choose anchor items for step two. It's going to give us a list of initial anchor items that we can turn around then and use for our actual diff test. So in order to get started, we first have to figure out how to link the groups onto the same metric. That's the first step. What we're doing, we're going to investigate invariance just to find candidate items to be used in the real invariance tests, according to that, that A5 approach from Mead and Wright. So let's take a look at this. We're going to run a new model here. We're going to use the multiple group command again, and we're going to analyze again that 2,000 person data set. We're going to use group again for the grouping variable. And now we've got added a, compared to the other free baseline model, we've added another kind of parameter here to this function called invariance. And the invariance, we're going to just concatenate, in other words, put all this together. All the items, so call names.dat will give you the names of every single item. So it's telling it use all the items and freely estimate that's what's going to be invariant. So invariant is going to be all the items, and you specify which items to be invariant, in other words, to be constrained to have the same item parameters as the first thing in this invariance thing here. So column.dat, this gives you all the names of all the items. It says make all the items invariant and make them all have the same item parameters. And then this is going to be for your latent factor. So this is going to say, free the means. So the groups are allowed to have free means and different means and free variances. So again, you can estimate freely the means and the variances for the two groups. So that's in contrast to before, right? Before the groups had equal factor means and equal factor variances. They were both 0 and 1, and then the item parameters sort of all varied around that. And here we're doing the opposite, right? The item parameters are all constrained to be the same, but the factor, means and variances are freely estimated. So let's run that. I probably should have started running that while I was chatting here. Didn't take very long though, and we can again look at the coefficients. And if you look at the coefficients this time, what you should see is that they are identical. So if you kind of look at this, look at item 1, 1.123, and for A1, let's look at D3 is negative 1.310. And we go down and look for group 2. You can see exactly the same thing here. That should be the case for all the items because all of them were constrained to be equal. Now, this model is going to have quite a bit of misfit, right? Because you are constraining item parameters to be the same when what they really want to do is be a little bit different. Remember, the item parameters are estimated in a way that they optimize model fit. So the item parameters, when you run them without the constraints in each group, will take on whatever values they want to in order to give you the best possible fit of your model. Here, what you've said is don't do that. You have to be the same across the two groups. So they're going to take on suboptimal values like we talked about in the other video. And that's what's happening here in this very first step. We've got a constrained baseline model, and we can, again, kind of print those out here. And you can see, since they're the same for the two groups, I've just said give it to me for just the first group and get rid of the other stuff there. So this is just the parameters coming back from that, from this statement here. And we're going to save that as constrained parameters. So we've just kind of saved that as an object. You look over here and it's got their items and it's got all the constrained parameters. And we can put that in a manuscript or tech report or what have you too. Okay, so now that we've got a baseline model to work from, we actually need to compare it to a diff model. So if you remember from our previous lecture, what you do in the likelihood ratio test is you run a separate model for each and every item. So to test item 1, what we would do is we would free the parameters for item 1, but keep the constraints for all the other items, and we would run that model and get a fit. And that model would fit slightly better or about the same as the constrained baseline model, where all the item parameters, including item 1, are constrained to be the same across groups. And so we do that, we run those two models and we compare the fit of those two models using chi-square, with the degrees of freedom is equal to however many things you're estimating. In this case, it'd be 1, 2, 3, 4 things. So that's what we're going to do. And the nice thing about the MERT package is it automates this for us. So previously, what you would have to do is you would have, however many items you have, you would have 15 items, you'd have 15 lines of code. And actually more than that, you'd have 15 different sections of code. And each section of code would evaluate diff for one item and one item only. So you'd run the model, you'd then compute the difference and fit from the baseline model, and you'd look that up in a chi-square table, and you would do that for each of your 15 items. That doesn't scale real well. So if you've got, a really big test or something like that, you get very sloppy code. And it's very handy that what the MERT package is doing with this diff statement is it is automating. This diff statement's like a function that basically automates running multiple models. And in each run, the item parameters for one and only one item are freed up compared to that constrained baseline model. So when you run the diff command, what we're going to tell it, and you could look at the documentation for the specifics here, but tell it that we're going to use as a starting point the model constraint, the baseline model where all the item parameters are constrained to be equal. And we tell it which item parameters we want to free in each run, and we're actually going to free all of them, the A parameter and the D parameters. You don't have to do this. You could just pick out one or more parameters, or just the Ds, or just the As, or what have you. And the scheme we're using here is drop. In other words, we're telling it we're using more of a drop sequence where we start with the most constrained possible item, and then we're dropping some of those constraints as we go through. Again, take a look at the documentation for the MERT package if you want to kind of figure out what all these things are here. And then the sequence stat, honestly, I'll have to look that up and see what that is. I cannot. Okay, so I just looked this up in the documentation, and the seq.stat, this like the sequence statistic, this is just a p-value you want to use. So we're going to use 0.05 here. If you wanted to be a little more conservative, since you're running 15 tests, you could use a Bonferroni, really conservative, or you could just make it like 0.01. It's pretty common, but we're going to stick with 0.05 here, a little bit more liberal. And because we want to be a little more, keep in mind you're testing misfit of the model, right? So we're going to test items. We're gonna by having a higher p-value, a 0.05 p-value, we're not going to allow a whole lot of misfit there. So if you use like a p.001, right, there could be more misfit in there, and it won't show up as significant because again, it's testing misfit, not fit. So we're going to run that, and again, should have started this earlier. So this one takes a little longer because you're not just running one model, like the baseline model. What you're running here is actually a bunch of models, right? You're running at least one item, a model per item, and we're testing that compared to the other one. So if you look at the output you get here, and I did save that as an object called diff.drop, but also printed it out on the screen here. That's what the little parentheses do. And it shows you the fit compared to the baseline model of this model and the chi-square. So the actual likelihood ratio test is right here, right? It's the chi-square statistic in this column, and the degrees of freedom, which is just going to be the number of parameters you're estimating, and the p-value over here in this rightmost column. So what you can see is some of these items had significance, which means they don't really fit. They fit, significantly better than the constrained baseline model, which means you actually have diff. So a p less than 0.05 means you've got diff. We know from our simulation that items 13 through 15 have diff, and sure enough, you see those all come up as very significant, right? They've got really big chi-squares, very low p-values, but other items come up as significant too, like this one and that one by p.05, yada, yada, yada. So a lot of different items here come up as significant. This is a really, this all others as anchors approach. You can see it flagged way more items for diff than we actually had. And there's a reason for that. So the likelihood ratio test is actually, fairly sensitive to sample size, kind of like a t-test. If you have a really big sample size and you run a t-test, you're going to detect really small differences. And the same is true with likelihood ratio test. The likelihood ratio test here, what you can see is with these big samples, even items that don't really have any diff, we know that because we simulated the items, and the item parameters we specified manually, you still see some dip. And that's why, all others as anchors is not really a great approach to use to detect dip because it flags way too many items, a lot of false positives, right? You might say. Um, so that's why we're not stopping here. We're not going to say, okay, we're done now. We used all others as anchors, and we have a bunch of diff, and our scale looks like it's terrible. Let's quit. That's not what we're doing. We're using that A5 approach that Mead and Wright recommended. And so what they said to do is to first rule out as anchors any item that has significant diff. So item 1 would be removed for consideration, item 3, item 5, item 8, yada, yada, yada. And just look at the ones that are left that did not have diff in this initial analysis. So I would not even report this in a manuscript. I would just say, here are some potential items, here are the items that did not show diff in this run, because you don't want the reader to get confused and think this is your actual test of diff. Because yeah, it is a test of diff, but we know it's suboptimal. We know it's flagged way too many items, so we don't want to actually mislead the reader to think that this item has diff. It's really just has diff in this first initial round where we're trying to purify our scale down and find the right anchor items. So next up is this function get diff items, and that's the one I wrote. It's totally optional. You don't need it. You could just look at this output I'm looking at right here and figure out which items have diff and which items don't. But all this item does is it takes this output, this diff.drop that we just saved. It takes that. It takes a p-value, and it takes the item parameters that we estimated earlier, and it just tables things up kind of nicely. So I'm going to go up here. I actually forgot to actually save this in, so I'm going to read this in. You can see it'll give you some warnings. It's just keeping, I've got some, a bunch of stuff here. Just keep the chi-square, get rid of the AIC and the BIC and all that stuff, yada, 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 and just return things kind of tidied up. And I'm not going to go through that line by line. So let's go back down here and run this, and you can see what it does here. It basically just organizes things a little more tidily. It says here are your diff items, and it puts those in kind of one list. And here's your no diff items, and it puts those in a different list, right? And then it'll give you any warnings that you might have. There's no warnings here, so that comes out. You don't have to worry about that. So essentially what it's saying is these are the no diff items that you need to choose from to make your anchor items. So if we're going to choose items to be anchors, we could have had up to 15 items here. We only have 5, and the Mead and Wright methods recommends choosing up to 5 that have high A parameters. So in this case, we're actually just going to keep all 5 of them because we have 5 non-diff items this first time around. But if we had, for example, if this had come out where we have like 10 potential anchor items, we would just keep the 5 with the highest A value. So the other thing this function does, not only does it sort out diff versus no diff, it sorts them by A parameter. So the idea is if you had a whole bunch of candidate items, you could just take the first 5 on this list and call it done and move on to the next phase here. Okay, now that we've identified some anchor items, the goal in step 2 is to actually test the non-anchor items for diff. Again, you cannot test anchor items for diff. They're assumed to be equivalent across groups, assumed to be free of diff, and so we can't test those. So we don't want to choose too many items as anchors because they don't get tested for diff. And so it's really better to choose only as many as you have to, so you get this second test for diff with those items, and that way you don't have any kind of false negatives. So anchor items are assumed to be free from diff. They're not tested. We're going to use the A5 approach, which is where you find up to 5, it doesn't have to be 5, but up to 5 items that are appearingly or apparently free from diff, and you then test the remaining items for diff. So in this case, we're actually going to flip the baseline and the comparison model from step 1. So remember in step 1, the all others as anchors, the baseline model was a fully constrained model. where then you freed item parameters to test the item for diff. This time we're going to do the opposite. The baseline model has the anchors constrained. Their item parameters are the same across groups, but all the other items are freely estimated. And then to test the items for diff, we're going to then constrain the item parameters for just one item to be equal across groups. So let's say you've got 5 anchor items out of 15 total items. The baseline model is going to have the 5 anchor items constrained across group, the other 10 items free to vary across group, and then the augmented model is going to have 6 items constrained across groups, the 5 anchor items plus the one we're testing, and you're going to repeat that process for each one, each of the items in order to test them for diff. And this is the final test for diff that we're doing. So which brings us to our next phase. So now we're going to move in. Now that we know which items we're going to use as anchor items, we're actually going to move into a phase where we are doing our proper likelihood ratio test. So let's take a look at what we're doing here. So the first thing we do is we need to manually specify what our anchor items are. So first off, we're going to read in the name of all of our items into an object, and item names is just call names.dat. If you want to look at that, it's just a vector of all 15 item names. And then we're going to specify the names of the anchor items. So in the MERT package, you have to give the item names, the anchor items by name, not by position or anything else, at least the way I know how to do it. I don't want to say that Phil doesn't have that in there, but to my understanding, that's what you have to do. So the items names are, we have to specify which anchor items we want. So I didn't automate this, we're just going to manually do it. You can see this list has items 2, 4, 2, 4, 6, 7, and 9. 2, 4, 6, 7, and 9. And so that's what we're going to specify here as our anchor items. So if we run this, well, now we have a list of our 5 anchor items. And again, the whole point of this is you wouldn't do everything on this no diff list. If you had 10 things on this list, you would just pick the first 5 with the highest A parameters. Where items with high A parameters give you a lot of information, right? They're considered good items. And then what we're going to do is we're going to test the rest of the items for diff. And like we said in the previous lecture, you cannot test anchor items for diff. You have to assume they are diff-free. And you test every other item. So what I've done here is I've specified all the other items to be tested for diff. So 1, and since 2 is an anchor item, it's not included. 3, 4 is an anchor item, so it's not included. 5, 8, and then 10 through 15. All right, so these are the ones we're going to test for diff. These we're going to assume are diff-free because they are anchor items. So let's take a look at that. So now what we're going to do is we're going to totally discard everything we've done up until this point, right? We're going to forget all about that initial run. We're not going to make anything further of those results. And what we've got going here forward are the actual results of your likelihood ratio test using the A5 approach. So we're going to specify a new baseline model. And we're going to use an anchor item approach now. So we're going to call the multi-group function again on our data. Model equal 1 means one factor. Group equals group is the same as before. And then now in variance, we're only going to hold invariant those anchor items. And we're going to, again, freely estimate the means and the variances of the latent factors for the 2 groups. Okay. And we're going to run the coefficients again. And actually, if I remove this, I'm just going to run this here. Let me do that part, and we'll get rid of that second part there, which reduce things down. It shows you what they are for both groups. And what you can see, hopefully, is the anchor items have the same item parameters, but the other items don't. That's what should have happened. So let's take a look. Our item 1 was not an anchor item in the baseline model. It's freely estimated. So the item parameters here should differ across the 2 groups. And if we go up here, what you see is item 1, sure enough, you have different numbers here than you have here, because there's no constraint on those items to be estimated with the same item parameters. Okay, but item 2 was an item anchor, so or an anchor item, sorry. So item 2, we should see the same numbers here, 1.209, and here, right? That's what we should see to be the same, 2.613, 2.613, yeah, so they're exactly the same. So this is our new baseline model. So and only the anchor items are constrained to be the same here. Okay. Okay. So what we're going to do this time is to run another round of diff analyses. Okay. And this time it's going to work a little differently. So last time our baseline model was fully constrained, right? We were using the all others as anchors. The baseline model, everything was constrained. And then to run the LR test, what we did is we freed the item parameters for the item in question, and we evaluated it at the chi-square. This time what we're doing is we're using the anchor item model, where only the anchor item parameters are constrained to be equal across groups. So to test an item, we're going to run that anchor model, and then we're going to add a constraint this time. So to test item 1 for diff, we're going to use that baseline model where only the anchor items are constrained to be the same, and item 1 was allowed to differ across groups. And we're going to compare it to a model where item 1 is also constrained to be the same across groups. So it's a different approach, right? Instead of loosening a constraint and comparing fit, we're going to add a constraint. And you're adding a constraint where you are testing each of the candidate items here, these test items, right? You're adding a constraint one at a time on these items in order to be the same across groups. So these items right here, these are always constrained to be the same. And in each subsequent run, these are going to be added to the list of constraints. So that's what the diff thing is doing. Again, the diff function is really powerful, really helpful. It saves you from doing a ton of individual analyses. So a big thanks to Phil for writing the package with that in there. So again, the diff is going to run a bunch of models for us to test item 1. It's going to compare the model where only these items are constrained to these items plus item 1. It's going to compute chi-square, it's going to report that, and then it's going to move on and do the same thing, comparing a model with all of these items to these items plus item 3. And it's going to repeat that process for all the items. I, again, should have been running that while I was chatting, because this does take a minute or two sometimes. But that's kind of the point here. So it's an unusual approach. You kind of start with an all others as anchors approach, just to get a list of potential items, and then you actually run the proper diff test, right? And I did a couple things different here. I actually said plot diff equal true this time, and you tell it again which items you want to test. It's automatically going to add constraints. That's sort of the default. Whereas up here, we use the scheme equal drop to say loosen constraints. We're going to go with the default this time, and it's going to add those constraints every time through. And then we're actually plotting the diff. And if you look at the trace lines here, you can actually see the items that were detected, for some of the items that were detected as diff, gives you the focal and referent group item parameters for that, the category response curve. I would probably, this is not really manuscript quality. I'd probably do something a little different to actually publish it, and like we did in some of the earlier kind of stuff in the semester, but it's pretty useful nonetheless. And the last thing we're going to do is we're going to run the get diff items command again. That's that homemade function we loaded in up front. And it's going to just summarize out again which are the diff items, which are the no diff items. Now, when you look down here, you'll see we're missing a bunch of items. And that's because the anchor items have to be assumed to be free from diff. So the anchor items are not listed here at all because they didn't get tested at all. They were just always part of the baseline model. The items that did get tested were all the other items, right? The 1, 3, 5, if you go back up here, 8, and 10 through 15. And what you find when you do this is you get exactly the right result. Remember, the nice thing about using simulated data is that we know which items are diff, right? We manually set the item parameters to be different for items 13, 14, and 15. And this particular method in this case came out and found exactly that, right? You get big chi-squares, you get p-values of 0, and you get diff for those items, and you don't see diff over here for these items. Again, we were using 0.05. With this many tests, you might want to use a p equal 0.01 because the likelihood ratio test is, again, very sensitive to sample size. So if you've got really big samples, you are slightly likely to detect non-diff items as diff. And we saw that big time in the other earlier run, right? And that's why we didn't use that run. Whereas here we are, we've got rid of that, but you still might occasionally, it may not work out perfectly every time. You could probably change that seed number and do a bunch of different ones. And sometimes you'll see, usually these will be detected, but sometimes some of these items will come out as diff items as well. And again, that's the nature of the likelihood ratio test. If you lower the sample size, you'd be less likely to see false positives.